Welcome to the Big Data Group Assignment presentation. My name is Tiff Loto and I'm gonna present task 1. This task focused on the nearest neighbor search. First, I will discuss the project objectives, followed by the 3 methods we implemented and our final performance results. The core challenge of the nearest neighbor search is to implement search methods to find the nearest neighbor in the 2D datasets. For our project, we used the shop dataset, which contains 150,000 points, representing shop locations. Our query volume consists of 200 user locations, and for each of these 200 users, we need to find a single closest shop on a 2D map. Our ultimate goal is to achieve minimum search time with 100% accuracy. Our first approach is the sequential scan. This is our baseline approach, and it is the simplest possible way to find a neighbor. The algorithm just calculates the Euclidean distance from the user query point to every single point in the dataset. Because it checks every point, the time complexity per query is O of n, where n is the number of data points, and in our case, it's 150,000. The main characteristics of this method is that it is extremely slow. It is highly inefficient for large datasets due to exhaustive and redundant calculations. It works, but we need a much smarter solution for big data. To fix the speed problem, we implemented a second method, the branch and bound algorithm. That algorithm is using a spatial index approach with an R tree. Instead of a flat list, we built an R tree that groups our 150,000 shops into minimum bounding rectangles. And through testing, we found that a node capacity of 30 gives us the optimal performance. The main advantage here is pruning. During the search, we visit the closest boxes first, and if the minimum distance to a whole box is farther than our current best found shop, we skip that entire group of points completely. This reduces calculation massively by cutting off parts of the map we don't need to check. To improve the performance even further, we use the branch and bound with the divide and conquer method. Here, a partitioning strategy is a spatial midpoint split. We look at the total width of the map along the x dimension, calculate the geographical center, and divide the data set into 2 halves. By doing this, we reduce the total tree depth, and we combine the power of splitting data with the pruning efficiency of R trees. This structure is very fast because it reduces the height of our tree, and theoretically, it's parallelizable, but that is something we did not implement, but which could be a further improvement. Let's look closer at the logic behind our divide and conquer approach. In a classical divide and conquer approach, you divide the data, build independent R trees, solve the subproblems separately, and compare the final results at the end. However, we implemented an optimized approach using cross-tree pruning. Instead of doing 2 completely separated searches, we pass a single p-best object through both trees sequentially. First, we search the left subtree, then we search the right subtree, and use the best found distance bound to prune the remaining search space. So we use the result of the left subtree for pruning in the right subtree. This cross-tree sharing gave us a little efficient gain. Now let's look at our final runtime results. Our baseline sequential scan required 5.16 seconds to complete the entire workload. When we switch to method 2, the standard branch and bound algorithm, the execution time drops dramatically to just 0.009 seconds. If we calculate the speed up ratio, we observe a massive speedup of over 500 times. For method 3, our branch and bound with divide and conquer, the execution time was only 0.01 seconds. This results in a speedup ratio of roughly 449. An interesting observation here is that method 2 is slightly faster. One reason for that could be the computational overhead introduced by the divide and conquer approach. For a dataset of this size, the overhead might be slightly larger. But however, the most important takeaway is that both R tree methods perform exceptionally well and easily beating the sequential scan.
Hello, my name is Andre, and I was responsible for task 2. In this part, I implemented Skyline Search on the City2 dataset, which contained 300,000 homes. Each home is represented by a 2D point. The X value is the total home cost, and the Y value is the price per square meter. In this problem, lower values are better for both dimensions. The reason we use Skyline Search instead of nearest neighbor is that buyers don't have one exact target point. They want to see every reasonable trade-off. So the goal is to return all homes that are not dominated by another one. The key rule is dominance. Point A dominates point B if A's X is less than or equal to B's X, and Y's value is also less than or equal to B's Y value. At least one of those values also needs to be strictly lower. In normal words, if another home is at least as good on both criteria and better on one of them, then we don't need to keep the dominated one. The same rule was applied on all three methods. The difference is not the skyline definition, but how efficiently we pass through the search. The first method we applied was sequential scan. This is our brute force baseline. For each candidate point, I compared it against every other point in the dataset. If any other point dominates it, the candidate is discarded. If no other point dominates it, then we can add it to our skyline list. This method was useful because it's simple and gives us a baseline, but it's also extremely inefficient because in the worst case, it compares every pair of points. That gives us an O(n) squared time complexity. Method 2, we used BBS, branch and bound skyline. This was using an R tree. The R tree groups nearby points into minimum bounding rectangles or MBRs. BBS keeps the priority list called H, sorted by minimum distance to the origin. For a normal point, minimum distance is based on the points X and Y. For an MBR, the minimum distance uses the lower left corner because that is the best possible place inside the rectangle. The important part is the pruning rule. If the lower left corner of an MBR is already dominated by a skyline point, then every point inside that MBR is also dominated or worse. So we can skip that whole rectangle instead of checking every point. That's where most of our speedup comes from. The third method combines BBS with divide and conquer. First, I sorted the dataset by our X value, split it into left and right halves. Then I built a separate R tree for each half and run BBS on each one. After that, we can combine our two skyline results. The left skyline is kept because the left side has the smaller X values. For the right skyline, each point is checked against the left. If a left skyline point dominates it, it is then removed. Otherwise, it stays in our final skyline, like this orange dot here. So, this method reduces the problem into smaller parts first, then merges the partial skyline results. The results show us that all three methods found the same 16 skyline homes. That's an important highlight because it means the faster methods are still returning the same correct result as the sequential baseline. The sequential scan took us just under 2 seconds. BBS took 0.0012 seconds, giving us around a 1600x increase, 1600x. The speedup comes mostly from the pruning as mentioned before. Sequential scan checks points directly, while BBS can skip our entire sections of an MBR once its lower left corner is already cleared. For BBS and the divide and conquer approach, I timed only the surge phase after the R tree had already been built. On this dataset, the plain BBS is already around 1 millisecond, so splitting the data did not show a noticeable extra gain. However, we can assume that if the dataset was more complex, maybe divide and conquer would show a better result there. To summarize, our sequential scan is the simple and useful baseline, but it's too slow at scale. BBS is much faster because of the R tree letting us prune whole rectangles instead of checking every point one by one. BBS with divide and conquer uses the same BBS logic, but splits the data first and then screens the right skyline against the left. The main takeaway is that R tree's pruning is giving us most of the heavy lifting. It gives the same results, but with much less work to do.
Hi, I'm Gwen. My part of this project was Task 3 Project Report. So there are three pieces in my session. Case 1 is the nearest neighbor, where we're looking for a single closest point to a query. Case 2 is the skyline, where instead of one answer, we want a whole set of best option. And finally, I will finish with a comparison with the both. First, case 1. I built an R3 on 10 points with a maximum capacity of 4 and 3 per node. Inserting points is straightforward until a leaf takes its fifth entry, then if overflow and has to split. When that happens, I pick the split that gives the smallest total parameter across the two new blocks, and if there is a tie, I break it towards the most partial separated region. 3 splits later, we end up with the 4 leaves, and you can see the boxes here. U1 through U4 sitting under the roof. Now the search itself, which is interesting part. The curl is the red point queue. We visit the leaves in order of how close they are to queue. Nearest first, always remember. So we start with the 2 close leaf. In one of them, point P8 gives us a distance of 2.83. That's our first best guess. Then we move to the next leaf and P10 comes in a 1.41, a new better best. And there's where the pruning pays off. And the 2 remaining leaves have miles of 3.61 and 4.0. Both are far away than our current best of 1.41, which means nothing inside them could possibly be closer. So we threw them both away without even looking inside. The dotted circle on the right is our 1.41 search radius. The answer is P10, and 5 of the 10 points were never even examined. The same problem also extends naturally to a divide and conquer setup, which is useful to run it in parallel. I split the data down the middle at x equals 5 and run branch and bound on each half independently. The left half gives us its best point at 3.16 and the right half gives us P10 at 1.41. I take the better of 2, that is 1.41. Then we certify it with boundary check. The query sits 3 units away from divided line. And our best distance is only 1.41. Since 1.41 is less than 3, nothing on the other side of line could possibly be closer. So P10 is confirmed as the global nearest neighbor. Moving on to case 2, the skyline. So what is skyline? Skyline is what we call non-dominated set. The key idea is dominance. A point is dominated if some other point is at least as good on both axes, and strictly better on at one at least. So we are looking for the points that minimize both x and y, so the smaller the better. Anything that isn't dominated by something else stays in the skyline. For our 15 points here, that sets turn out to be P3, P4, P7, P9, and P14. And the red dots you see tracing the frontier here. So the algorithm that we use in branch and bound skyline or BBS like before, it searches the three best first, but this time it is key on distance to the origin, which is H, rather than to a query point. We pop entry of a priority queue one at one a time. When a pop point, if it isn't dominated by anything already in our skyline, we add into it. The pruning rules, it is the interesting differences. We skip a whole node when its lower left corner is best possibly a point and is already dominated by something in the skyline. So you can see here on the left side exactly happening. So one node corner at 6, 7 is dominated by P9, and the another one is 4, 12 is dominated by P3. So both entire sub 3 get skipped, and there's 6 points that never have to touch. And there's what we arrive at the same skyline set, as previous mentioned. Skylines also extend to divide and conquer, so I split at x equal 8 and run BBS on each half. The left half produce 4 skyline points and the right half produce 2. To merge them, we use the screening steps because every point in the right half has a larger x, and the only points that has to be knocked out are the right hand ones, and that's what happened. P8 turned to be dominated by P3, so we get it removed, while P14 survived. The merge result is exactly the same skyline that we found before, which is a nice confirmation that both methods agree. So lastly, how do we compare them? So they share a lot the same thing, such as same R3 and same best first traversal. But what differences are? Nearest neighbor measures everything against a moving query point, such as Q, while skyline measure against the fixed origin. And NN prunes using a decent threshold that gets tighter as a search improves, and crucially, it can stop early. The moment the closest things left is farther than the best is already found. BPS prunes using dominance instead. And because skyline is a set rather than a single answer, it can't stop early. It has to work all the way through the queue. So in conclusion, same underlying machinery, but two generating different jobs. Thank you.